All right, so let's go ahead and work our way through this problem that we started to do last time in lecture 2b, but didn't have time to finish up. So the problem is that we have a sprinter that's starting from rest and accelerates at a constant rate of 2.5 meters per second squared until she reaches a top speed of 15 meters per second. And after that, she's going to continue to run at this top speed of 15 meters per second until she finishes her 100-meter race. Right. The question is, how long does it take her to complete the entire race? So first thing, strategy part 0 is actually to sketch the problem. It's always best to have a picture because a picture really helps clarify things. So we have a sprinter Sally. She's going to start at x equal to 0. We are free to choose our origin anywhere. This is the most logical place to choose it. So we'll choose initial position to be 0. And then she's going to start running, and she's going to accelerate at a rate of 2.5 meters per second squared until she reaches some point, some unknown point at which she will reach her top speed. From that point on, she maintains that top speed until she finishes the race. Okay? So as you can see, this problem naturally breaks down into two parts. A part where she's accelerating, and a part where until she gets to a top speed, and a part of the problem that involves running at a fixed speed for the remaining distance. And we don't quite know what that remaining distance is yet, but we'll get there. So as I said, we can break the problem into two parts: accelerating from rest to top speed and running at a constant top speed until the end point. So first thing we're going to do is to determine how long it takes her to accelerate from 0 to 15 meters per second. Right. The next thing we're going to do is, once we know how long it took her to get that far, to get up to this speed, we can calculate how far she gets during that acceleration. Right? So then we know, once we know that position, we will have figured out where this breakpoint is located, where she reaches top speed. Then, because we know this point and how far she's already run, and we know that she has to run a total of 100 meters, we'll be able to know what the distance remaining is. We'll know how much further she has to run at that top speed, and then it's straightforward to calculate the time that it takes to run that second distance. And then we add up the two times, and we are done. We know the total time. Okay, this is of course not the only way to solve this problem. You could imagine a variety of other ways. This is probably the most straightforward way. And so we're going to focus on this strategy. So let's determine how long in time it takes her to accelerate from 0 to 15 meters per second. Right? We have, because this is a 1D kinematic equation, it's basically running along a line, and we're changing speed and we're changing position. This is a 1D kinematics equation. So our natural instinct is to use one of the kinematic equations. The question is, which one? Right? So let's eliminate some possibilities from logic. Right? We know our goal is to determine time, duration. Right? And we're given acceleration, and we're given certain velocities. Right? So because we're interested in time, we can probably eliminate any equation that doesn't include time in it, right? Because that won't help us get to where we're trying to go. Right? So we're going to exclude this one, which tells us the relationship between velocities and positions. But for the strategy we are pursuing, which is that we want to first start by figuring out the time it takes to do something, this won't give us the kind of information we want. We'll also eliminate any equations that require position information, especially for this first half, because for this first half, we weren't told how far she had gone by the time she reaches top speed. If we had been given that information, then maybe these equations would be useful, but we don't know XF. We don't know the final position. We do for the whole problem, but not for the first part, right? Remember, we're dealing with part A right now. We're only trying to figure out how long it takes her to get to that the point where she has reached top speed. Right? And we don't know where that mystery point is. And we don't know how long it takes her. So we have too many unknowns to use this equation. Right? Same thing here. Too many unknowns. But here, this last equation is just right, because the only thing we're missing is time. Right? We know the initial velocity. She started from rest. We're told that the top speed that we're trying to reach is 15 meters per second, and we're given her acceleration. She can accelerate at 2.5 meters per second squared, right? So the only thing missing is delta t. So this is the right equation for us because it's a single equation with a single unknown, and it happens to be the unknown that we are trying to solve. We're trying to find duration. So let's solve equation 1 for that duration. Right now it's written so that the duration is tucked over on this side, so we'll just do a little rearranging and get delta t, and I'm going to give it a subscript a because we're solving for just this first portion of this problem, right? That first half where she's accelerating to top speed. So the time for this first portion of this race is going to be the final velocity minus the initial velocity, because I'm bringing the initial velocity over onto this side, and then I divide by, that gives me a delta t is equal to vf minus vi, and then if I just divide both sides by a, then I get delta t by itself. Right? And again, I skip a couple lines of algebra here, but if any of you are having difficulty following, just write them out on paper yourself. Okay, so that's an equation that we're going to hold on to for now. Next, we're going to find the displacement, how far she has run during this acceleration to top speed, right? So now our current goal is to solve for a displacement. So we're trying to solve for a displacement, so any equation we're going to use had better have a delta x in it, or xf and xi at least, right? From which we can calculate delta x, sorry. And we already know the acceleration and the velocity, and now we know the time, right? So at this point, we have actually quite a few choices, right? The only one that's obviously not appropriate is this one, because it doesn't have any x's in it. It doesn't have any displacement, but it does have, and we've already used this equation, so likely we're not going to use it again for the exact same portion of the problem. All other three of these kinematic equations will allow us to calculate it because we have an abundance of information now. But let's stick with the most simple one. These two right here include a t squared or a v squared. This one is all linear. It's got no square root dependence. So although any of them will work, we'll stick with the easier one, and we'll take this second kinematic equation. Okay, so let's work with this equation and rearrange it so that we get a displacement, right? So xf minus xi is delta x. Again, the subscript a because we're still working in part A of this problem. And that gives us the sum, bring this over to the other side. This is equal to vi plus vf over 2 times delta t. And again, putting in the subscript a because this is just for the first part. Now we can go ahead and plug in some numbers to make life easy. Delta t from the previous page was vf minus vi over a, right? And that gives us 15 meters per second, our final velocity, minus 0 over the fact that she accelerates at 2.5 meters per second squared. That gives us a total of 15 divided by 2.5 is 6. So 6 seconds to get to top speed. How far does she get in this time? We plug into this equation. We have vf minus vi, that's again 15 minus 0, divided by 2, times by delta t, which we just calculated to be 6 seconds. 15 divided by 2 is 7.5. 7.5 times 6 is 45. Okay. So she moves 45 meters in 6 seconds, and by that time she's at top speed. Now the remainder of the problem is pretty straightforward. For part B, we just need to finish the race at this constant velocity. There's no acceleration, so vf and vi are the same for part B. And we already found that it took 45 meters to reach top speed, so the total amount of displacement left for her to cover, only the total amount of position difference that she's left to cover in part B is just that 100-meter race, minus the fact that she's already run 45 of it in getting up to speed, so she has 55 meters left to run at full speed. Now for zero acceleration, the kinematic equations that we have, these 4 equations, simplify down, right? In this case, this is simple. Vf is equal to Vi. That's just a statement that she stays at constant speed. That's not super helpful to us. This equation simplifies to VEF squared is equal to VI squared when this A goes to 0. It's also saying velocity stays the same. Still not important, but not helpful to us. These equations, on the other hand, because VI and VF are the same, this just becomes 2VI, right? Because you can just say VF is equal to VI. Times that by the half, and you're just left with VXI is equal to VI times delta t. This equation actually boils down to the exact same thing, right? XF is equal to VI delta t, and this term goes away, right? Okay, so these two equations boil down to telling us that delta x, XF minus XI is equal to V delta t, which we knew. This was something that was the total amount of displacement is just velocity times time, right? So that it was a long way to go about it, but I wanted to show you that you can still use the logic of I just need one of the kinematic equations, which one is relevant, okay? But if you could just kind of recognize that you needed this from the start, great, good for you. Okay, and this of course only applies when the acceleration is 0. So finally plugging in, we can rearrange the equation that we just had to solve for delta x. So if velocity is delta x over delta t, then delta x is equal to velocity times time. Sorry, that's what we started with. And now we can solve this for delta t, and delta t is delta x over v, right? Dividing both sides by v. And so now we get, plugging in the numbers, delta t for the second half of the race is delta x over velocity, which is now a constant 15 meters per second. So we take the 55 remaining meters, divide by 15 meters per second, and we get 3.667, again keeping a few extra sig figs than we need to avoid rounding errors. And finally, to get the total time, we just take the time that we solved for the first half, which was 6 seconds, and the time that we solved for the second half, which is 3.66, add them together, and then finally, for our final answer, report it in the correct number of sig figs. And we're done. All right.